everyone. Today's On Semiconductor Technology webinar. Our topic today is Get Started, Go Deep with the Motor Development Kit. I'm Matt Finesse with On Semiconductor, and I'll be your moderator today. If you have any technical difficulties during the session, you can click on the help icon at the top of your web page. And at the end of the webinar, we'll be holding a Q&A session to answer any questions that you have. So that means that during the webinar, you can just type your question into the chat box on the right side of your screen, and we'll answer any of them that you have in there at the end of the webinar. The webinar here will also be recorded, and we'll post it at onsemi.com, and you'll be notified via the email address that you registered with when the webinar is available. So the webinar will also be and the webinar is also sponsored by our distribution partners, Avnet, Avnet Silica, and EBV Electronic. So now let's meet today's presenters. Ali Hussein is Senior Manager for Strategy and Corporate Marketing, focusing on power electronics. He has previously worked in technical marketing at Fairchild Semiconductor and International Rectifier in various roles for 9 years. Ali is a Bachelor of Electrical Engineering and Bachelor of Economics from the University of Pennsylvania and a PhD in Electrical Engineering from the California Institute of Technology. And Michael Zapke has 30 years of experience in R&D and marketing roles, including project manager for large-scale ASIC and FPGA designs, head of systems engineering for telecom infrastructure equipment, and several platform management and technology management responsibilities. In 2013, Michael joined Xilinx, and he shaped innovation for industrial applications on FPGAs and SoCs at Xilinx in close cooperation with industry-leading development teams, research institutes, and customers. His main work areas are industrial networking, embedded control for industrial applications, and functional safety. So now, let me turn things over to the first presenter. Ali, the floor is yours.
Thanks very much, Matt. Let's get started. So what I'm going to do is talk a little bit about what is the MDK, the Motor Development Kit platform, and give you an idea of what our suite of power boards are, and then give you a quick getting started, a few getting started steps to help you see how easy it is to use out of the box. So what applications are we aiming for here? And we're really talking about industrial drive, and here's an example of a block diagram of an industrial drive where you've got a three-phase inverter connected to the motor, and then upstream of that, power factor correction, high voltage gate drivers, your feedback circuitry, and your input bridge. So we'll have various incarnations of those in these kits, and we're really aiming at things like robots and cobots, servo motors, high-powered variable frequency drives, and things like pumps and fans, commercial HVAC, for example. So all of these applications fit there. So what does it take really to be a supplier in this market? Well, you have to have a focus on the industrial market and have a comprehensive product portfolio with the leading quality supply chain and manufacturing network, which we have around the world, as well as application expertise so that your customers will be able to design and solve problems quickly and get going on their own application rather than struggling with getting the basics going. So that's what the MDK is really all about. Before we start, I really want to understand a little bit about your designs. And the first question here is, do you require a PFC stage in your design, in your motor drive design? So PFC stands for power factor correction. And it really depends usually on whether you're taking single phase or three-phase input from the line, and or how your power distribution is done in your factory or industrial facility. So take a little time, and there are various ways of doing power factor correction. You could do it with traditional boost. You can do something different like a totem pole, which is a newer topology. There are interleave topologies also, which reduce the voltage ripple. So I'll just give you guys maybe another 10-15 seconds to answer, and then I'll tell you the results. All right, so it's neck and neck here. We have over 40 answers, approaching, see, they keep coming in, so I can't stop here. Okay, 50 answers total. I'm going to give you the results. You can still keep submitting them if you want. About 56% of people say they need PFC in their motor drive design. 45% of people say no. So actually it changed, 55, keeps changing, sorry, 56 and 54. So about half and half. So again, it depends on your power level, it depends on your application. Let's go on the next poll question. So this is a little bit more complex. What is the biggest challenge in your motor drive design? Is it hardware, designing the hardware, dealing with the hardware aspect? Is it the cooling system and figuring out what are you going to do with any heat that's generated both by the power electronics, but also by the motor itself? Is it designing the algorithm? Do you need to have a complex algorithm or special functions in there? Is it the application software, the higher level controls that really interact the motor to the rest of your system and allow you to get the most out of your total application? Or is it something different? So I'll give you guys a few, maybe 10 more seconds, 15 more seconds. Sometimes challenges can even come from the application itself, and it's totally outside the motor drive, and the motor works fine, but you have some maybe resonance in your system that affects how your motor is going to operate. And sometimes you can deal with that with algorithms. All right, so we'll close the poll now. About 26% of people said hardware, 16% of people said cooling, 41% of people said algorithm, 17% has said application software, and apparently there's no other issues because other got 0 answers. So number 1 was algorithm, and then if we combine with that with application software, dealing with the software aspects is a major part. And so in the second half of this, Michael Zapke will tell you a little bit about the functionality and the capabilities of the Xilinx part that you can apply to those problems. So let's continue. Let me give you the high level of the motor development kit. The motor development kit consists of basically 2 boards in any implementation, which is the universal controller board, which is the control layer based on a Xilinx Zinc 7000 SoC, and then a power layer, which is a various application boards. So we are developing a suite of them. You can see a few of them there, where this includes the power stage, perhaps a PFC, and then auxiliary supply and all the interface electronics already. So once you put these 2 devices together, these 2 boards together, your controller board and your power board, you're ready to run a motor. Some of the targeted motors that we're interested here are BLDC motors, BLAC motors, switch reluctance motors, permanent magnet synchronous motors, induction motors, and pretty much any 3-phase motor is within the target of our boards here, depending on power level and voltage. And of course, the universal controller board is targeted toward a variety of topologies, both your standard 3-phase motor drive, if you're doing something like silicon carbide, where you need really fast calculations, it is appropriate for that, as well as 3-phase PFC, which really is a kind of 3-phase motor drive in a different algorithm slightly. Even more complex, where you're at a 3-phase PFC plus a 3-phase motor, or PFC plus LLC, like a DC charger for an automobile, or other more complex topologies like Viennas or multi-level topologies. So we're targeting a variety of applications. We've just started now with your basic motor inverters, but we'll be building up a bigger suite of these over time. And I'll show you some roadmap information as we go forward. Let me just talk a little bit about the universal controller board as a whole. Michael will talk more about the Xilinx Zinc and Xilinx tool chain. But the universal controller board has a 10-channel differential ADC based on our Semiconductor ADC chip, complementary PWM channels, a number of digital peripherals, as well as a USB to JTAG or UART interface, onboard Ethernet PHY, and USB, as well as plenty of memory and a micro SD card. What we've also done is we've taken care of the whole power tree. So you can see that we have input of 5 volts that is supplied actually from the power board. And then we on Semiconductor DC to DC regulators for all your step downs for the various rails that are required. And then as with the UCB, beyond the MDK, of course, you can implement various advanced control strategies, your diagnostics and preventative maintenance, and even more higher level kind of machine learning, deep learning, and your AI. That's the next generation in really advanced control technologies. Also, out of the box, the ON Semiconductor MDK has a graphical user interface to get you started quickly. You can do a basic volts per hertz control or do an FOC control and change the speed and output power and measure and evaluate the various internal variables that are happening in your control, as well as telemetry measurements such as voltage, module temperature, and motor current. So this allows you to really get going quickly, check that everything's working, and really get right into your application. So let's talk a little bit about the various power boards that we have available. The 1 kilowatt compact IPM board gives you a complete system from AC line to interleave PFC and your inverter stage. So you can see from the input, we've got ON Semiconductor bridge rectifier and our PFC based on our super junction MOSFETs, as well as our interleave PFC controller. Then the inverter stage is comprised of our compact intelligent power module, which includes the gate drivers internally, so that you have a nice compact and thermally well-defined power stage. In addition, we've got our DC to DC regulator there to supply the auxiliary voltages, as well as comparators and sense amplifiers to give your feedback to the control layer. So this is already available and orderable from our website, either as an individual board or as a kit with the universal controller board. The other one that's available now is our SPM31 4 kilowatt power board. This one's based on our 4 kilowatt SPM31 package IPM. Again, that contains gate drivers and inverter stage. And then we have the similar voltage step downs for all the supplies required, as well as op amps and comparators for safety and feedback to the universal controller board. This one does not contain a PFC because at the higher power levels, often if you're taking it off a three-phase line, you may do a passive PFC, or the power distribution in your industrial facility may already be DC. So then you can just connect it into your DC bus and hook up your motor and get going. Coming up later this year in Q3, we'll be releasing a series of lower voltage and mid voltage BLDC motor driver power boards. These are based on our discrete MOSFET family, but anywhere from input from 10 volts up to 100 volts, depending on your application. For example, if you have a battery operated forklift or a robot, these are the perfect boards for hooking up to your power, to your motors, and getting your application going. So look for these as they come out. And here's our roadmap, where I've shown already the two available boards, the 1 kilowatt and 4 kilowatt based on our IPMs. Our power MOSFET boards, a family of 4, depending on your voltage level. And then early next year, we'll be releasing a 5 kilowatt transfer molded PIM eval board. So the transfer molded PIM is a new type of package released by ON Semiconductor recently that is a power integrated module. So that means it contains only the power devices, not the gate drivers. Gate drivers are kept externally. And what it does is that rather than doing your traditional gel filled package, this is an overmolded package so that you have higher reliability, longer life, and is actually more compact and better thermal performance. Also coming in the future on our roadmap is a silicon carbide MOSFET-based inverter, a totem pole PFC front end that would be appropriate to connect to the 4 kilowatt board, as well as more IPM and transfer molded PIM-based power boards. So again, you may not find exactly what you're looking for here, but once you get started with it, you get going with the UCB, then it's easy to do your next motor based on our growing suite of power boards. So you just tailor the power board to your particular voltage and power level, and then you can get going quickly. Again, I keep saying that that's really the focus of this, is to get you going quickly so that you're not struggling getting your motor running. You really can move on to your application stuff. So let me just take a couple slides to talk about how to get started with the MDK, show you how easy it is. You start by connecting the UCB to the power board, and make sure you download the software, connect your PC to the universal controller board via UART. And then once you provide power to the voltage to the power board, you're going to see that your communication is connected on your screen in our GUI. And then you can set up your volts per hertz or FOC parameters and go ahead and try to run your motor. Once you have your motor running, you can start the motor and view your data. You can see this inset where we're showing a motor running and the speed changing over time. Then you can connect your loads, you can measure your temperature, you can measure efficiency, and now you're actually doing application work, right? And then the next step would be to get into the advanced control algorithms and application software. That's the type of thing that Michael will talk about the capabilities in the next part of the webinar. So I appreciate your attention. For more information about the MDK, you can visit our landing page onsemi.com/MDK. And there you'll find information about all the existing power boards, how to order them either individually or as a package with the UCB. And I thank you for your attention. And now I'll pass it over to Michael for more detailed information on Xilinx and how to work with the Xilinx Zinc 7000.
Thank you very much, Ali. Well, that was really a lot of flexibility with a growing number of power boards with semiconductor technology on it that Ali has just shown in his presentation about the motor development kit. The solution can go wide to many different applications. And I want now to talk more about the go deep aspect that you see here on this page in the next 20 minutes. My name is Michael Zapke, Industry Lead at Xilinx, and of course I'm glad that Semiconductor invited me today to talk to you. It's a pleasure. Before you start the development of a new motor control solution, you always face a platform question, a platform that has the capability to grow with your needs, and that is applicable for a wider range of target products in most cases required. One element here at the top left is performance, or high performance. The platform shall give you the right engine for the right task. So that means if you need real-time capability, a real-time engine, then it should be a deterministic architecture that you're using. And if you need an application, then you shall have the required processing performance and I/O performance. And task-specific accelerators in particular, of course, for industrial, help you to fine-tune the performance. Second, here at the bottom left, that's adaptable. A programmable platform shall allow the customization of the processing function. And, of course, the interfacing shall be also customizable. Ideally, the platform shall allow you for any kind of automation and avoid any limitation concerning access to data that you create in your system, and also concerning the integration of processing. Virtualization, that can be a decisive factor for reusing existing assets, existing applications, for instance, when you add a hypervisor in the design. And here also at the bottom left, machine learning will enter into more and more devices in industry. An ideal platform allows you for the integration of edge analytics and even the integration of neural networks for inference. Number 3 is for small and rugged. Miniaturization is often a development target, but do not forget that integration also helps often to reduce system-level cost. And it's also important, the reduction of chip-to-chip communication avoids issues with signal integrity that you have on board sometimes, and it reduces also efforts for a complex serialization and deserialization between chips. That can be rather convenient for a safety concept. Also, on-chip RAM enables to collect data from the attached motor system for an intelligent monitoring and for maintenance. And that means to get transparency concerning the state of your device at every time and in real time. And number 4 here on this chart is networked. With programmable IOs, you're capable to make your product match the neighborhood. And if you have more sensors, then you can basically just add additional interfaces to a good platform. If you have a proprietary interface, probably a legacy interface, then a good platform lets you program that with the right electrical characteristics. And not to forget, for network chips, also security features are key. In particular, if you are connected to the industrial Internet of Things, then you can benefit from features like a hardware root of trust in a chip that uses a ROM that nobody can influence. And no wonder, I talk about the platform on chip today with programmable logic and with microcontrollers, and we call that a Xilinx, often an adaptive system on chip. With the MDK, with the motor development kit, you have seen in the last 25 minutes such a device in the context of a power stage. This device is Xilinx, or it's from Xilinx Sync 7000. In the combination, it gives a highly performing and efficient motor development platform. It allows for miniaturization by integrating as much as possible in a single chip. The growing range of ON Semiconductor's power boards makes it versatile and capable for new transistor technologies. The MDK comes with a universal control board. We call that also UCB. You've seen that stays the same across all these power boards that have been in the first presentation and that belong to the MDK lineup. The UCB is from Trans Electronics in Germany, and it contains Sync 7000 as the processing device. Modern design methods using Xilinx design tools make you fast and efficient when you create your own design. Vitis, you see that here and at the bottom of this page. Vitis is the name of the unified software that comes with tools to develop on high-level programming languages, and that supports also model-based design with popular environments like MATLAB Simulink. And even frameworks with Pythons are possible. I remember you voted with 41% also for the topic of the implementation, the algorithm. So that gives you a level of freedom and also a good path to create your algorithm. Traditionally, an electric drive is based on a multi-chip solution. And it's typical to have a DSP function for control loops for modulation, a CPU for other protocols that are running next to that, and sometimes a communication device to exchange data with the next higher hierarchy. In this picture, it's a PLC. And the power stage connects to the DSP or to the modulator and receives and this gray part here receives some or all sensor data that come back from the power stage. So it's 3 dark chips here on this page and additional support like external DRAM, power, clock, and other peripherals. Today, this all can be integrated, or at least the 3 bigger chips can be integrated so that DSP, CPU, and interfacing resides on the same silicon. Also added custom functions like monitoring, like diagnosis, maybe for safety, can be on the same chip. connectivity is not necessarily only to the next network level like a PLC. In the industrial Internet of Things, it can work in more complex scenarios, like also providing direct cloud connectivity with related protocols. And with a small board that contains the system on chip and the voltages, some DDR memory, and clock sources, it becomes a complete controller, which is small size and versatile, and all on a system on module. And that is what we call the UCB. And as you have seen, actually, that is the architecture of the MDK. On Semiconductor's power boards connect to the UCB and form the target architecture with Xilinx 7000 as a system on chip in the middle. That is a platform that fulfills most of the requirements that I talked about on my first slide. I mentioned several times programmable logic, and many of you know what an FPGA is, but for those who don't, every Xilinx device has programmable logic. That is what is also known as FPGA. An FPGA is basically a combination of Boolean functions to a digital circuit, and that is compiled on a uniform fabric architecture with thousands of lookup tables and registers in between those. Compilers work with multiple languages for that. There are hardware description languages that can be used, but also algorithms in C or C++ or System C can be used, and even higher level frameworks like frameworks for machine learning and edge analytics can be the entry point for such an FPGA development. You can create basically any kind of digital logic with that kind of primitives that you see here on the right. And because all functions, when you do it like this, have dedicated lookup tables, they're dedicated resources and registers, you can instantiate functions in parallel to each other without any interference between those. That's good for multi-access. That's ideal for anything that must be deterministic. And that is what stands behind execute in parallel here in the bullet list at the bottom. Built-in memories and built-in programmable DSP blocks increase also the versatility. Just imagine that you stream cyclic data from your motor into RAM that is on the same silicon and process it in another block also on the same silicon next to that. That avoids a limitation that a dedicated ASSP-like system on chip might give you by its architecture. In this case, it's all freely programmable and therefore perfect for a development kit. Also, I/Os can assume different functions and different electrical characteristics by programming, and the characteristics can be different speed, can be different swing, can be single-ended or differential. And not only that, there are also analog digital converters, ADCs, integrated in such a device. And finally, there can be one or more homogeneous or heterogeneous processors in such a device. You remember my statement from the beginning, right engine for the right task. You can insert a RISC processor, soft core in these elements, and you can add in addition, or you can use in addition ARM processors, which are on the chip as hard macros anyway. All that is in parallel, all with own resources, so you can reduce the interference between each other. And I think now it's the right time to zoom a bit into the chip that I'm talking about. I used here a pretty simple diagram, but I believe that makes it clear. The yellow part is the programmable logic, this FPGA part, and that's a place for the lookup tables, the registers, the DSPs, the block RAMs, and also the ADCs. The number in the red boxes show you examples for sizes, and this scales across a product family from small to large, while it always keeps the same architecture. This architecture includes also this gray part here at the bottom left. And that is a processing system that consists of 1 or 2 ARM Cortex-A9 processor cores with peripherals and some additional on-chip memory. And there are also other Xilinx SoC system on chip families with other ARM cores. But for today, let us stick to this particular architecture because this particular thing is a device on the universal control board, which is part of the NDK. And not to forget, both areas, the gray and the yellow, are well connected. The processing system communicates with the programmable logic using AMBER AXI. In general, it is a concept to use AXI for all blocks to communicate with each other. Even if you reassemble a system, then you have the AXI communication in between everything. And that is what makes a platform. We call that IP-centric design. We think in blocks which are connected through AXI. And next, on the next page, I will talk about mapping of a motor control solution to this. And the flexibility of the chip architecture gives you a good level of freedom. And no doubt that the easy way, the simple way, is to run a field-oriented control on the ARM core in the gray part, and nothing speaks against it. That is not unusual at all, and that works pretty well. Actually, that's a starting point for the MDK as well. But today, I would like to look also a little bit forward, what you can do with that as a next step, and answer this go deep question from the beginning. So why not putting motor control also into the yellow part? That means into the programmable logic. That is something that we at Xilinx have some experience with over many years, over more than 10 years. Control loops for torque control, or for speed control, or for position control can be in dedicated logic in the yellow part of the architecture and control the modulator, which is in the same domain, so that you can connect various power stage semiconductor technologies to that. Now you might ask where the advantage is to not do that simply in the microprocessor, but put it in the yellow part into the programmable logic. First, there are more blocks for concurrent functions that you can add. For instance, there's a possibility to add a motor model here at the bottom in the middle. That is some kind of, that can be a basis for creating an estimator for sensorless control, or that can also act as a digital twin within the motor control device. With that, you have a powerful way to monitor that the dynamic behavior is in its limit, and that even in a real-time fashion, even strictly cycle-oriented. Digital twins are a strong trend in industrial IoT currently. Lots of white papers about that. And even if you don't need that, the use of dedicated logic instead of the microprocessor can help when you upgrade to technologies that benefit from faster control. For instance, for an upgrade to silicon carbide. You heard about that in Ali's presentation already. While it is not a big deal to run cycles of 50 microseconds for one axis in a microcontroller, it is more difficult to reach probably 10 microseconds or even below in a predictable way just with software in a microprocessor. And I will show you some control loop times that can be achieved with logic durations in a moment on an extra diagram. Important for the industrial Internet IoT is data input, collecting data. Even in a small configuration on the chip, that was really this page before, even in a small configuration on this chip, there is access to much data from the outside, like current feedback that you can get from the motor or encoder feedback that you can collect. You can stream this all into internal block RAM, internal memory, and that is called big data, and is the basis for decision making inside the processor. At the end of my presentation today, you will see an example for what that all can be used. And now I come back to the page that I showed you shortly already. Here I put what I just said in a kind of stack. An architecture like the universal control board can be used to collect data from a motor and customize it by increasing the number of motors which are connected and increasing the amount of data that can be processed simply in parallel. You can capture, let us assume, 3 bytes of information every 50 microseconds, every control loop cycle. And if you do that, then you reach already 60 kilobyte per second. And that is 3.6 megabyte per minute, or 5.2 gigabyte per day. So for each motor, that is a lot of data that you can collect from a very simple system. And that means that you will never forward this all data or upload that to a remote machine, to a server. Instead, you will try to process data where they have been captured and while they are captured at the same time. So here in the stack, there is data filtering and reconciliation that does it best with dedicated custom blocks in logic, and that is a green part of the stack. The red stack levels stand for the application of a digital model and an optimization based on a comparison with the digital model. And that is the digital twin that I was talking about before. And finally, the gray box above that is a piece of software that changes the setting to react smartly on deviations programmed with a predefined strategy. The data to store and upload deviations from a digital motor model is possible then to a cloud, and you can reduce the number of, or the amount of data when you do that comparison with a model significantly. What you store as historic data in a server or in a cloud is much, much less, and therefore much, much cheaper concerning operational cost. And a user interface that runs on an ARM processor in such a device helps you also to have a solution that you can log in through an Ethernet network so that you can complete with that an industrial IoT ready product, a typical Industry 4.0 product. And you know, I promised to talk about the go deep aspect. And that is what you can do with the UCB, but it doesn't come out of the box when you just start a motor development kit in the easy way that you have seen in the first part of the presentation by Ali. That is exactly what you can do to differentiate then by using the Xilinx design flow when you want to customize that. And let me show you a diagram with the engineering software with the tool environment on the next page. You can fill the chip with functionality by using Xilinx Vitis Unified Software Platform. The basis, the red bar here in this diagram, is Vivado, which processes your design and places and routes the basic elements on the silicon. And that is a classical entry point for hardware developers. And there's also extensions for C code development, which we call high-level synthesis. Because a system on chip has microprocessors, there is also an SDK, the light blue element. Peter Linux tools are there to work with Linux and with Yocto, and that is the SDK in our Vitis. And then there are 2 dark blue bars at an even higher level. Applications can be developed in a high-level language, and there are methods to move functions from a processor to the hardware or to use libraries for programming. The highest level, that is Vitis AI, takes data from machine learning frameworks like TensorFlow and translates this in inference models for the system on chip. So even if you say you don't need that all when you just develop a motor, believe me, it's useful to have that capability for a future-proof platform that has an entry point for hardware developers, for firmware developers, for application developers, and for data scientists. That is Industrial Internet of Things. So I mentioned that you can develop in C or C++, and here is a diagram that shows you the principle. If you have an algorithm in C code, you can use high-level synthesis to transfer it to a hardware description language that you can place and route with our tools. Our target is to support always an IP-centric design for which you can, or into which you can put your assets. And that means that you can create your differentiating designs and also port them to other devices. And the UCB and the MDK and the motor development kit can be a brilliant starting point to do that, to develop such assets. I also talked briefly about model-based design before. And that is another option to design a control algorithm. MATLAB Simulink is likely the most common way for designing. Simulink has interfaces like the HDL coder, and there are also optimized block libraries for Xilinx designs that come with what we call the model composer. The best way to use advanced model-based design for efficient circuitry on the chip is that, and processor in the loop is also an option for testing the design, the model with target hardware. Now I want to come back to the topic performance and show you some achievable cycle times for control loops when you use the capability of the device. Torque control can be as short as 1.6 microseconds in IP, and that is something that we have already developed with partners, and we have also used these practices, these solutions together with on Semiconductor for a special use case in the past. Speed loops are approximately twice as long in the 3 to 4 microseconds range when you do them in hardware. The full chain to the output to a communication bus can be optimized to 16 microseconds, as fast as the fastest networks, real-time networks are. And that all is deterministic. It's not an optimum that can be achieved sometimes or most of the times. It's really predictable. And when it's designed for that, it will always work. So it's no magic. It is simply in hardware, and it has dedicated resources. So when we have that option to add circuits without impacting the performance of other circuits in the yellow part, then it's also possible to add analytics or machine learning. You remember this diagram, and now I added this red block here at the left side. I admit that we will quickly reach the limits of the universal control board. So here I show you a little bit of the going even deeper or even beyond the UCB. But anyway, UCB is a good starting point. You have the chance always to step up to larger devices for your target application. I spoke about the amount of data that you collect when sensor data are received in a cyclic manner at a very fast pace. So why not collecting samples over a predefined period and convert them in such a device to an image simply? You can measure, for instance, the currents that come from the motor and from two of the windings, create a two-dimensional chart with the current for alpha on the x-axis and the current for beta on the y-axis. And after collecting probably 2,000 samples, you can classify the resulting image with an inference machine. You can do that in the same device that controls the motor. Virtually everything works locally, no support from an external machine needed. And the red box creates a result, notifies it to the built-in ARM core, and a decision can also be made locally here in the blue part and communicated to the outside. It's really a drastic optimization, a simplification that uses the capability of automation with knowing the status of all the sensors real time. When I talked about an image that could look like this, the simplification is obvious on this chart. You don't assess the individual point on the picture. You create an image, probably 20 images per second, and use this to derive actions. And mathematic models can be used to create data sets, to do the training, to classify good or bad and distinguish both from each other, the green and the red stage. And that brings me to the end of my part of the presentation. So as a recap, the design software options are there. Create the logic on the basic red block, create OS and low-level software firmware in the SDK, create your applications, your differentiation, and derive offloading using Vitis, and create analytics functions on the top level with Vitis AI. And now the summary, here some advantages at a glance. The platform that we used in the MDK is an economic solution with a system on chip. The right semiconductor technology and it's optimal for fast control, and that also improves energy efficiency. Most of what you've seen, with the exception of the high-end neural networks, is possible with what you see today in the MDK from ON Semiconductor. It also allows for high productivity. Productivity means engineering efficiency using the Xilinx advanced design flow with Vivado, Vitis, and Vitis AI. Edge analytics becomes possible next to the motor, exactly in the device with motor control, by streaming data into chip internal RAM, data filtering and reconciliation, motor models for digital twins, and neural networks for classification. The latter in the successor of the Xing 7000 family that is on UCB. Model-based design is possible with third-party software like MATLAB Simulink. Above all, it's a long-living platform. Systems on chip have a long lifespan because a newer generation does not replace a former generation. The application of the same chip in several market segments that makes it possible to use the programmability to tailor it for different applications. And because it's programmable, it can also keep up with the evolution without having the need for introducing new chips every few years. The forthcoming silicon carbide, for instance, when there are silicon carbide-based power boards, this architecture allows that they can be supported and the advantages can be used because we're flexible enough with that kind of technology. The last keyword here is safety. The integration in one chip improves signal integrity at interfaces and reduces the need for circuitry for mapping and demapping and for serialization and deserialization. Xilinx has a safety certified Vivado toolchain that certifies us against 61508 up to SIL 3, and the certification of the newest Vitis version, that is a version from the year 2020, is in the works. Well, and that brings me to the end of my part of the presentation. I want to express my thanks for your interest in the webinar and your time to listen and watch it. And of course, also I want to thank ON Semiconductor that they asked me to speak to you during this event. And now for the questions and answers, Matt, please take over again.
Thank you for going through your presentation as well. And thank you everybody for asking the questions that you have here. So we've got a good selection of them. So I'm just going to jump right in and start asking you guys the questions that we have. So the first one actually is a double question. It came in early in the presentation. They have two questions. One, are there any available or planned kits for 2 to 3 engines? And are there any available or planned sets for 1, 2, or 3 brushless motors?
So we don't have any plans right now to be able to control more than one motor with the UCB. I believe that the resources are there to do so. I'll let Michael comment, how many motors would be the maximum number maybe you could run with the UCB?
Yeah, that depends a little bit, of course, what you do exactly. We have experience with up to 4 motors in exactly that device that is on the UCB. Here it's, of course, by intent. We want to create here, the MDK is a solution that allows you to create the implementation for a power stage, and you have the capability when you do a chip down solution to add more. But to give you a feeling, of course, when you add interface blocks and probably a motor model, then I think putting up to 4 blocks for motor control into such a device is possible. And of course, you have always the capability to run things in the ARM core, and that is why I shy away from saying you have a limit. It really depends on what you're doing.
From a hardware point of view, I'd say it's a little bit challenging to make a multi-motor board just because we don't know what your application is, whether you want 1 high power, 1 low power, or 2 of the same, or even 1 or even 2 different ones for robotics versus more of an industrial drive application.
All right, thank you both. So jump into the next question here. What is the advantage of using AI in the control algorithm for a motor?
Shall I answer?
Well, I'm a power guy, so I'll throw it over to the control guy over there.
Yeah. So of course, machine learning and artificial intelligence, and you have seen that I mentioned again and again the word edge analytics here, is one of the topics that helps you to do things like predictive maintenance, for instance, to compare the real physics behavior with your expectation, and to work also with an outcome or with sensor data that come back that you didn't prepare, where you don't have a particular threshold. You remember I showed you some diagrams, and showing a distortion of a circle or analyzing a distortion of a circle, that is easier by saying that you have an artificial intelligence approach than saying I look at every individual sample and look what the relation to the sample before and the sample after is. So you have a different way of approaching how to find out if a gearbox, if gears are probably seeing wear and tear, or if a bearing is not working anymore, or if your load is different than what you expect. And that is what the power of artificial intelligence is. And it helps you also a little bit really to see what is connected. When you talk about electric vehicles, you can probably think about measuring if something happens with the axis or with the tires or so. So I think the opportunities to use that electronic way of monitoring connected things are infinite with AI.
You guys may have touched on it at the end of each of your presentations, but what are the stages to develop and test the power module / board?
Well, I mean, the first step is to power it up and make sure you have communication, that everything's kind of working properly, and you have your supply voltages in place. Then the next step would be to actually run your motor and make sure your motor's running, that it responds to speed commands, etc. And then you can actually start attaching a load and testing it under load, testing the thermal aspects of your design. And then that's where you probably want to start to get into algorithm and application control, and that's your go deep.
So the next one we have here, are there any examples of control applications, BLDC, BLAC, PV inverters, etc., using SoC available?
Yeah, maybe I can answer that. I mentioned in one sentence that on Semiconductor and Xilinx work together. Even beyond that, we have already made an example where we created an SoC integrated solution that uses the programmable logic. And of course, I'm also happy to tell more about the implementations. Here it is, I would say, you see here already a pretty good portfolio that works with implementations which are following the normal requirements for a motor control with MOSFETs, but we can go with silicon carbide, which is ahead in next year, to something that we have already in our devices. And I would say, if you're interested into the details, because that goes pretty far, it would be good if you contact your person on Semiconductor or at the distributor. It's easy for on Semiconductor to contact me, and then we can go into the details. I can show you what we have done and also what we have done with on Semiconductor.
So we got a kind of a two-part question, but I'll just include the first one on here because I think it kind of encompasses a number of things. But we have an interesting question here. So what would happen, hypothetically, if 100 robots with motors work at the same time? Would they create any noise? Would that create any issues?
100 robots with motors work at the same.
Shall I answer? I can give a fast answer.
I don't quite understand the question, but go ahead, Michael. Take a
So
stab at it.
of course we have switching noise. So actually that is a PWM or another modulation, and that modulation creates noise, and that noise can be a big problem with the setup. And you ask a very interesting question, because with speeding up control loops and with using also methods to do more calculations in a cycle, you can use methods to reduce the switching noise that you have in the system, and therefore also reduce EMI problems from switching that is done by the transistors on the power stage. There are, for instance, what we are currently investigating in is a pretty well-known technology like model predictive control. That is something, of course, that can be done. Here we also go, of course, beyond what you get directly when you just take this board on the table. But that is really something with what you can differentiate. And when you remember that I said you can add dedicated hardware to your modulation and to the field-oriented control or to model predictive control or whatever you're doing, then you have the chance also to bring in your algorithm. And I can also tell you there are solutions available, not all for free and just for download, but there are solutions available at least as a starter. It needs a bit domain know-how in the end to create your own solution with that, but I believe it's easier than with a predefined PWM modulator when you do it with a system on chip. I make a lot of advertisement for our devices now.
I mean, of course, layout and you know, your physical aspects have a big impact on electrical noise, and it also depends. You know, if you have 100 motors, they're probably distributed around, so you might have long cables, and that is also a challenge for noise. So all of those need to be carefully characterized and properly shielded, depending on, again, power levels, how long you're traveling, and how well you do your layout.
All right, thank you guys both. Thanks for answering the question. Got another one here. Do the MDKs use an external ADC? Is the Zinc built-in XADC sufficient for power control in servo drives?
So there is an external ADC on the UCB. I'll let Michael answer about the built-in.
Also, that depends on your requirements. Well, 12-bit and 1 megasample is basically what we can reach with that technology with an integrated ADC. And we sometimes also go for solutions which use an external ADC. For simple or for current measurement, that is possible. Actually, I am not 100% sure if you can access the ADC also directly on the UCB. I need to look it up if the board is designed like that. But you see, you have a good capability. If you need to have more precision, then probably you go beyond it with an external ADC so that you have a digital signal at the system on chip.
All right. All right, thank you both. Thank you, Michael.
The answer is sufficient. It is sufficient in principle, so you can run a motor. We've done it ourselves. That works.
No. Thank you, Michael. So we are short on time here, going towards the end of the webinar right now. So I'll just ask you guys one last question before we close out. So the question I have here for the last one, how do we generate the reference current in BLDC motors, modeling for speed control? So talking about the reference current in BLDC motors modeling.
So this is an algorithm question, right? I mean, you can answer it, or I can try to answer it.
Yeah. So I talked about the speed loop, and the speed loop is nothing else but always changing the current by using a PWM or a different modulation. So you monitor, assuming that you have a sensor system like here, you monitor the encoder, and your control, your regulation is very fast. So that is how you do that on a digital level. So basically, you create the torque that exactly compensates everything, that changes your speed, and that allows you to reach the speed pretty fast.
All right. Well, thank you, Michael, for the question. Thank you, Ali, as well, for going through your questions earlier as well. And thank you, everybody, for asking the questions. Sorry that we didn't get a chance to go through all of them. We will get back to you through email for any questions that we weren't able to get to. But yeah, thank you, everybody, for attending. Thank you, Michael and Ali, for going through your presentations. And everybody, have a great rest of your day.
Thank you very much.